Today we're going to be doing the level N chapter 4 notes. So this lesson or this entire chapter is practically just questions. We don't have any new explanations. It's all things we've taken before. It's just they're, I guess, giving us more information or adding to our information about them. They start off this chapter with two definitions: molar concentration and one definition. It's the number of moles of solute per liter. And now the rest of the questions here are calculations. So we start off with CQD2. What mass of H2SO4 is needed to prepare 500 centimeter cubed, which is the same as 0.5 liters, because you divide centimeter cubed, divide by 1,000 to get liters, of 2 molar solution. So this is your concentration, and this is your volume. So what mass is needed? Now to find the mass, we know that mass equals 2 moles times molar mass. So our moles are, and we know that also moles, this is moles, equals to CV, or concentration V. So what we're gonna do is you're gonna multiply the 0.5 times 2 to get your moles, and you're gonna multiply it by the molar mass, which is 98. 2 times 0.5 is gonna be 1 times 98, which is gonna give you 98 grams, and that is your mass needed to prepare. Now, you have 25 centimeter cubed, which is 25 times 10 to the power of negative 3, aka 0.025 liters of 0.4 concentration salt solution. They were evaporated to dryness, and then 1.11 grams of the salt was left as residue. So what are they asking? They're asking for the molar mass of the salt. Now, we need to find the moles of the solution given. So, what did they give us in the question? We need to find out what we were given. So we were given a volume of 250 and a concentration of 0.4 and a mass of 1.11. What we need is big M. We know that big M equals 2 moles over mass. Or is it mass over moles? Wait, it's N equals M over M. So M equals M over N. My bad, I switched the equation. It's M over N. And we know that my bad, because the equation they put here was confusing me for a while. Anyways, yeah, we know N is CV. So our molar mass is equal to the 1.11 grams over concentration, which is 0.4, times the volume, which is 250 divided 1,000, which is 0.025. This all should give you 111 grams per mole, which is our answer. Now for part C, what volume of this concentration HCl solution should contain, what volume do you need of this solution that has 3.65 grams? So again, we know that, what do we have here? We need the volume. So CV equals N, which is the same as M over M. Now we want V. So to get V, it's you add C to the bottom, because you're dividing by C. Right? Should be right. Yeah. Like I said, I don't know what equations are they using here. That's why I was confused. So what we put up is the mass, which is 3.65 grams, over molar mass, which is 36.5, times our concentration, which was given as 2. Put them all into your calculator and we should be getting 0.05, which is 50 centimeters cubed. Now for CQD 3. A sample contains 2.12 grams of Na2CO3, was dissolved in 500 centimeter solution. Calculate the concentration of all ions present. So what do we do here? First of all, we have to calculate the concentration of the entire thing. And we know concentration equals to mass over moles. Is it? Yeah. Again, I have absolutely no idea what they're naming their variables. So, anyways. Yeah, it's moles over volume, which is the same as mass. Moles over volume. Wait, isn't it N equals CV? So V, they want, C equals N over V. N over V, yeah. It's N over volume. N is the same as M over molar mass. So it's M over MV. So our mass is 2.12. Our molar mass is Na2. Okay, so we get it from here. It's 106 times the concentrate or the volume, which is 500 centimeters squared. We always have to use it in decimeter, so 0.5. When you do all of that, you get equal to 0.04, and of course, be careful for significant figures. Now you're gonna say, okay, what's after that? Okay, what you do is, I'm gonna write somewhere down here. I'll delete it later. So Na2CO3 is made out of two ions. It's made out of two Na plus and one CO3 minus, right? Yeah. So if the entire thing has 0.04 concentration, this is gonna have 2 moles of the concentration. So this is gonna be 0.08, and this has 1 mole. 1 times 0.04 is still 0.04 moles. See, this is how they solve it here. 1 mole gives you this, so 2 moles gives you double. So Na is gonna have 0.08. Let me erase to show you. And CO3 is gonna have 0.04. Now let's move on to the example. AlCl3 was a solid. AlCl3 was a solid dissolved in enough water to get Cl minus to be 0.2. Find Al3. Now, if we have AlCl, it's annoying. AlCl3, we know it dissociates into Al3 plus and 3 Cl minuses. And we have the concentration of the 3 Cl's to be 0.2. So 3 has a concentration of, my gosh, the page is annoying, 0.2. We want, how much does 1 have? 1 mole. How much concentration does it have? So you just cross multiply 0.2 divided by 3 gives you 0.067 molar. By the way, guys, like for this entire video, I'm just gonna be explaining what's the AMARC scheme written because it's all solving and we've all done it before. What mass of CuSO4 chemically combined with 5H2O, which is copper sulfate, hydrated copper sulfate, is needed to produce 200 milliliters, aka as 0.2 liters, of 0.25 concentration copper sulfate solution. Okay, so the molar mass of the copper sulfate is gonna be 249.5 because you need to add the water, 5 times 18. So we know that mass, because they're asking for mass equals moles times molar mass. Moles is 0.2 times 0.25. Yeah, they all did it here. Times the molar mass you have, multiply everything together, and we should get 13 grams. And that's it for this question, or this page, I mean, my bad. And that's it for this question. Also, let me move on to the next page. So, there's no explanation in this entire chapter, or the chapter before it, or the chapter after it, I think. Anyways, let's move on to the next question. 150 milliliters, so 0.15 liters of 0.5 molar NaOH was mixed with 250 milliliters of 0.3 molar BaOH2. What's the molarity of OH minus in the final solution? When they ask for molarity, they mean what's the concentration. So now we need to find the concentration of the OH from NaOH. And we know that NaOH, I'm going to write it up here, NaOH, this associates to form Na plus OH minus. What we already know from a previous question is the number of the concentration, or the number of moles in this, is the same as the number of moles in each ion multiplied by the coefficient. So here you have 0.15 times, or you have 150 times 0.5. I don't know why they kept it in millimoles here. I'd prefer to put it in normal moles. So 0.15 times 0.5 is supposed to give us 0.750, I think. But let me check on my calculator. Yeah, 0.075 moles. 0.075. So Na is gonna also have 0.075, and so is OH. We only care about OH because we didn't ask about Na. So we solved the first part. Now you do the same for BaOH2. Now the only problem here is now this dissociates into Ba2 plus and 2 OH minus. So you need to find 0.250 times 0.3, which is gonna be 0.150 or 0.15. No, it's not. 0.250 times 0.3 is gonna give us 0.075 also. So this has 0.075. Ba is also gonna have 0.075, but this is gonna have that times 2 because there's 2 OHs, and 2 of it was gonna make 0.15. So now we have 0.075 moles of this and 0.15 moles of that. Now the total is them added together, of course. So it's gonna be 0.225 moles. I think we can use moles, it's fine. Yeah, you can use moles. And we need to find total volume. Total volume is gonna be volume 1, which is 0.15 liters, plus volume 2, which is 0.250 liters. So when you add them together, you're supposed to get 0.4, no, I got a wrong number, wait. 0.15 plus 0.25. What? 150 plus 250, طيب. It gives us 400. I don't know why here it says it gives you 500. I think there was a mistake here in calculation, because total volume isn't 500. 150 plus 250 gives you 400. So I think there was a mistake here, but I'll make sure later, and if there's a mistake, or I made a mistake now in solving, I will make another video to explain it. But as far as I know, this is wrong because it's supposed to be 400 milliliters. And then you divide the number you got, which is the 225 millimoles, or 0.225, divide by 0.4. That's what it's supposed to be. I think this question is wrong, but like I said, I'll check, and if it's right, I'll make another video to explain it. Anyways, let's move on to the next question. What's the concentration present in 0.10 molar of Na2CO3. We already know that Na2CO3 dissociates in 2 Na and 1 CO3. So find the number of, so we don't need to find the number of moles because we need the concentrations. So you're gonna, if this has 0.10, this is 0.10 times 2, so 0.20, and this is 0.10. And that's practically it. This is what's under my writing. See? 0.20 and 0.10. Calculate the number of moles of all ions present in 50 centimeter cubed, so 0.05 liters of 0.1 molar of PbCH3COO2 solution. So once you see something like this, we need to know it dissociates into, I'm gonna do it right down here, PbCH3COO2 dissociates into Pb2 plus and 2CH3COO minus. Okay, so now we need to find the moles of the full thing, which is 0.05 times 1.1, which is going to give you 5 times 10 power negative 3. And then we do what we've been doing for the past 7 trillion questions. This is going to stay the same because Pb has a coefficient of 1, and this you're going to multiply it with the coefficient of 2, so you're going to get double whatever it is. And like I said, these entire questions, all these questions are just repeating each other, same exact concepts. It's just the regional likes putting a million examples and then gets none of them in the exam. Anyways, CQD4. A sample containing 25 centimeter cubed of 0.2 molar NaCl solution was mixed with 75 centimeter cubed of 0.02 molar CaCl solution. Calculate the concentration of the Cl ions present in the solution, and you need to know that no reactions take place when these two are mixed. So, what do we know? We know that we have two different solutions, both containing Cl. We need to find the concentration of Cl in both of these solutions so we can solve. Now, NaCl, we have, how many moles of NaCl do we have? We have NaCl, we're going to do 0.2 times our volume. We're going to get that it has 5 times 10 power negative 3 moles for NaCl. So Na plus is going to have that, and Cl minus is also going to have this. But we don't care about Na now, we care about the Cl minus. So 5 times 10 power negative 3 for this one. Now we need to find for CaCl2. CaCl2 gets deassociated into Ca2 plus and 2Cl minus. CaCl2 is going to have moles of 1.5 times 10 power negative 3. Once we multiply it here by 2 though. So here it's going to have 2 times 1.5 times 10 power negative 3, which is supposed to be 3 times 10 power negative 3, but yeah. So now what we're going to do is we're going to add all of our values we got. You're going to add the number of moles and this together. Once you add them, like here, you get that they add up to 8 times 10 power negative 3 moles. Now we have our moles and we need to find total volume. Total volume is 25 centimeter plus 75 centimeter, making 100 centimeter cubed, which is 0.100 liters. So then you multiply, you divide moles by volume to get concentration. So 8 times 10 power negative 3 over 0.100 gives you 8 times 10 power negative 2 concentration, molarity. And that's how you get your final answer. Now let's move on to the next page. There's about 12 pages of solving, so now we're on page 27 and we finish at page 36. Now that's a lot of pages. Anyways, it's fine. Where were we? Kinda lost the page. We were here, right? Yeah. My bad. Anyways, a lab technician is asked to prepare 500 centimeters, so 0.5 liters of this concentration solution from a solution that has 6 molarity H2SO4 stock. Explain how you can do this. Now what we know is, you need to know this equation, C1V1 equals C2V2. So what we're gonna do is 0.5 times 0.5 equals concentration, which is 6 times V2. You're gonna get V2 equal to this number. Now 0.417, we need that much of the stock, because the stock, that's 6 molarity. Now we need to use a burette to take this exact amount of the 6 molarity acid. You put it into a volumetric flask that's 500 centimeter cubed. Why? Because you need to prepare this much. Now you need to already have about 50 in the milliliters of water in the volumetric flask already. Why? So you can add the acid straight to water, so it can start. Like, it's not a really important step, but like just put it always. Then you add enough water till your flask until it's touching the bottom of the meniscus, is at the etched line or tangent to the etched neck, and then you shake it to mix the water with the solution, and that is it. Now example 6. 150 milliliters of 0.5 molarity HCl is mixed with 50 milliliters of 0.3 HCl. Add the above solution, enough water to make the total volume 400. What's the molarity of the HCl in the final solution? So you need to find the HCl in solution 1, which is 0.15 times 0.5, 70, or they use millimoles. I don't like to, but sure. 0.075. It doesn't matter. Actually, let's use millimole. 75 millimole. In solution 2, you do the exact same thing. 50 times 0.3, you get 15 millimoles. When you add the two together, you get that the total is 90 millimoles. Now, you need the total volume to be 400 milliliters. So 90 divided by 400 is gonna give you 0.225, which we need for significant figures. All of these are in 2 significant figures, so our answer must also be in 2 significant figures, meaning it is 0.22 molar. And that is it. So all we need to do is just find total moles or find total volume and just keep dividing and adding. You only need to know the equations. N equals CV, N equals M over M, and CV equals CV. Anything else? I don't think there was anything else. Anyways, moving on. Enough water was added to 100 milliliters of 0.30 molar of CaBr2 to produce 500 milliliter solution. Calculate the concentration of ions in the final solution. Now, the amount of ions we have in CaBr2 are multiplying these two numbers together to get 30 millimoles. And then you need to find the concentration of CaBr2 by dividing it by the total volume, which is 500 given in the question. You get 0.06. Then, since CaBr2, it's gonna deassociate into Ca2 plus 2Br minus. So this molarity, it's gonna stay the same for Ca, but you have to multiply it by 2 for Br because there's 2 moles of it. And that's primarily it. These questions were all things we took back in grade 9, if you remember. And we took it also in the grade 10 material. We've taken it 2 times already. That's why this entire file is just solving. What volume of 18 molar H2SO4 is needed to prepare 200 milliliters of 2 molarity H2SO4? Again, CV over CV. CV equals CV. So CV, you need what volume? So volume 1 times 18 equals volume 2 which is 0.2 times 2. So 0.2 times 2 is 0.4. 0.4 divided 18, I'm assuming. Yeah, wait. Concentration 1. Yeah, here. Wait, why did they get 0. Where did they get the 1 from? Wait, let me reread the question. What volume of 18mH2SO4 is needed to prepare 200 milliliters of 2 mole H2SO4? Now, I think the numbers are... Why is it here 18 and here written 6? Is there a mistake? Guys, because I swear this is the first time I solved them, and I swear these aren't the numbers in the question. Even the moles of H2SO4 in the final is wrong. So, anyways, what you were supposed to do, my bad, my pen flew. You're supposed to find the volume now, and then, yeah, volume final is this much. And then you add it to... Oh yeah, by the way, I switched them. This is here supposed to have the 2 mil to 0.2 mil. And here you're supposed to have volume that's unknown. So 0.36 divided by 2, so 0.18, which is 180 milliliters. And then you're supposed to just subtract of how much you have volume, which here they put into as 20 instead of... The entire question is wrong, guys. So none of the given they actually used, so I was very confused. Anyways, it's fine. And now we need to read these. They're just some things, reminders. All group 1 salts are soluble. All nitrates, acetates, and ammonium salts are soluble. These were the solubility rules we took in chapter 3 and topic 11 in the grade 10 material. Precipitation reaction is one where a solid forms upon mixing. This was also in chapter 3. Acid-base, one where protons are transferred, where water is formed, because always it's protons and water is always formed when you react with an acid or a base. And redox is one where electrons are transferred, where it's oxidation or reduction. And the only new one is disproportionation reaction, which is one where the same species is getting oxidized and reduced at the same time. You're gonna say, what's the difference in redox? You always have things getting oxidized and reduced in redox. Yes, but here it's the same species. Like, let's say you had Na. Na is being reduced and oxidized in the same time. We've never taken this one before, but I don't know if they ask about it or we just need to know it by definition. I'm explaining, guys, by the way, I've never done a single AMS or periodic about these topics, so if you do have any extra information for if you did the periodics and AMSs, please do mention them in the comments. Anyways, identify what type of reaction is each of the following. 3Mg plus N2 gives you Mg3N2. This is redox. Why? Because this one from oxidation state 0 and this one from oxidation state 0 to each having an oxidation state, because you need to find the oxidation number of each, but each of them, when they're in a compound, they have a state. They don't become 0. So this is redox. Yeah, exactly. Mg is increasing from 0 to +2 and N2 is decreasing from 0 to -3. So now that's the first one. Now let's go on to the second one. Fe2 plus 2OH minus is Fe2OH. This is precipitation. Aqueous into solid. Now NH3 plus HCl. HCl is an acid, so immediately acid-base reaction. And acid-base reactions are never redox reactions. HCl is donating a proton and NH3 is accepting a proton, of course. Now here you have NaOH, also acid-base, because NaOH is a base. HCl is donating a proton, OH is accepting a proton. Now Cl2 and H2O gives you HOCl plus HCl. These are disproportionation reactions. All I know about it is that explanation. So Cl2 is being reduced from 0 to -1 and oxidized from 0 to +1. Cl2. Because they split the Cl into two different molecules. So one of these molecules has to be oxidized and the other one has to be reduced. Because here you have Cl2 and here they're each in a different one. That's how it can be both at the same time. Anyways, draw a particulate diagram that represents the solution formed when the two below are mixed. Do they actually want me to draw a diagram in the exam? Yeah, I'm gonna skip this because who's actually drawing in the exam? There's no written either way and it can't come to us as actually it could be select which of the following and they show you the diagrams. Anyways, what you need to know is this is an aqueous reaction and this is an aqueous reactions that are both two of them Ag with Cl2 produce a precipitate because silver with the halogens makes a precipitate. So we have to have a precipitate in the bottom and the rest just continue being like their normal states. They just react with each other. So all you need to know is this is a precipitation reaction because AgCl2 or AgCl, my bad, is a precipitate. Now, stoichiometric calculations of precipitation reactions. So what do they want? A solution is formed by mixing 1 liter and 1 molarity KCl with 1 liter and of 1 molarity PbNO3. Calculate the mass of PbCl2 that will form assuming a complete precipitation. So now we need to find the moles of KCl and the moles of PbNO3 too. Each one will have 1 mole because 1 times 1 gives you 1 in both cases. Yeah, see 1 mole for both. Now, NK plus KCl, K plus, Cl minus. No coefficients to multiply. So this will have 1 mole and this will have 1 mole. Abas, now here's the thing. PbNO3, 2. So it's going to dissociate into Pb2 plus, شو هاي Pa? Pb, my bad. And 2NO3 minus. So this is going to also stay 1 mole, but this is going to become 2 because you have 2 as the coefficient, see? And we need to find our volume total by adding all the volumes we have, which is 2 liters. And they want to calculate the mass. Mass equals moles over molar mass. And wait, no. Yeah. And we can replace moles by CV. So CV over molar mass gives you the mass, the concentration. What do they want, by the way? The mass, yeah, okay. So you find the moles. Wait, we have the moles. Wait, what do they need exactly? You find the limiting, yeah. Because, again, I didn't take this in class, so these are the first time I'm seeing these questions. You write the reaction because you're making Pb2 plus. Oh my god. Pb2 plus is the aqueous and Cl is the not it's both aqueous قصدي, but this is the كأنه على ضارب بعد الأيجي. المهم, it makes PbCl2, which is a solid precipitate. We know this because the solubility rules. Again, only lead and silver always make a precipitate with bromide, iodide, and chloride. So you write down your reaction, then you write down your moles. Here you have 1 mole and here you have 1 mole. When you divide by the smallest number of moles, which is should divide by smallest, you don't divide by smallest here. Here you divide by the coefficient and then you get the smallest. So this one's bigger, so this one's excess, and this one's smaller, so this one is limiting. Now you're gonna write a reaction with the limiting. Since Cl is limiting, you're gonna cross multiply the molar mass of PbCl2, or sorry, the mass. Was it given in the question? No, you're gonna multiply the molar mass. You're finding the mass. You're gonna multiply 1 by the molar mass divided by the moles of here, which is 2, because this is the limiting. You always multiply with the limiting, and then you get this as your answer. Wait, what? I think they're COO3. Where do we get CaCO3 from? Just cross multiply, guys, and you're gonna get, wait, let me do it on my calculator because there's something wrong with this file. Divide by 2, you get 139. Yeah, 139 exactly. But I don't get where they got the CaCO3 from. There was no CaCO3 in the equation, or was there? Yeah, there is absolutely no CaCO3 in the question. So anyways, it's fine. Now part B, calculate the molar concentration of all ions left in the solution. Here they named it part C. Yeah, the person who made this document was on something when they did, because I don't get it. Anyways, something fell. Anyways, KCl, we know it has 1 mole and the volume is 1 liter. And PbNO3, we also know it has 1 mole and the volume is 1 liter. What you're gonna do is you're gonna find the moles of the excess reagent left. We know excess reagent here is Pb. Since Pb is our excess reagent and we used to have 1 mole of it, how many moles are left? How do you find that? You minus by the limiting ratio, which is 0.5. You're gonna be left with 0.5. Then you find the concentration by dividing the moles by the volume, the total volume, which is 2 liters. And then you get 0.25 molarity. NO3 minus is what comes from the PbNO3 here. So you're gonna do 2 divided by 2 because we have here 2 moles of NaCO3. Remember, I said this splits up into Pb2 plus and 2NO3 minus. Since this is the case, you divide it by 2 to get 1 molarity, and K, because look, you're gonna find whatever is left. We use the K and we use the Pb and we use the Cl to make PbCl2. What's left is the K and the NO3. And the K, now we're gonna do the exact same thing but divide by 1 because its coefficient is 1. Anyways, let's move on. This question was way too long. The solving for al-fadi, like there's no reason why it shouldn't have been that long. Anyways, calculate the final concentration of ions when we have 50 milliliters of this much molarity AgNO3 and you mix it with 50 of this much molarity CaBr2. You need to find the moles of both by, again, the moles of Ag are equal to the moles of NO3 because you have 1 mole of one ion of each. So their moles are going to be equal to the entire thing. So you do 0.05 times, or they used 50 here because they want it in millimoles. You get 10 millimoles. You're going to find the one for Br and the one for Ca because you have 2 Brs and 1 Ca. Then you're going to get 10 millimoles for the... No, wait, it's 50 milliliters. So 50 times with 0.1 is 5 millimoles of Ca because you only have 1 mole of the ion, and you're gonna get 10 millimoles of Br because you have 2 moles of that ion. Then you divide it by the total volume to get the concentration. Total volume is 50 milliliters with 50 milliliters, so it's 100 milliliters. 10 millimoles by 100 milliliters gives you 0.10 molarity for NO3, and the same for Ca2+. You're gonna say, where did the Ag and Br go? Ag and Br make a precipitate, so they're not any ions left in the solution. They're reacting ions, they're not spectator ions. Ag and Br are in a reacting ratio of 1:1 and are present in equal amounts. Nothing is in excess, so Ag and Br are negligible. None of them are in excess. Usually you have to check for the excess one. Now calculate the final concentration of all ions when 150 milliliters of 1 molarity Na3PO4 is mixed with 150 milliliters of 1 molarity AgNO3. So here, I think we have 1 mole of everything other than Na. Na, you have 3 moles of Na plus here. That's the only one that has a coefficient. So we're just gonna we're gonna multiply 150 by 1 to get 150 millimoles of Ag, and the same for PO3 or PO4 3 minus, And Na, and NO3, by the way, it's with Ag, so it doesn't matter really. And Na, you're gonna multiply that exact same thing, but with 7 times 3, because we have 3 moles of Na. Now, we have the concentration of NO3 and the concentration of Na, since they're spectator ions. Our final precipitate should be AgP. It's AgPO4. So we need to write down the equation and find the excess. So 150 is for PO4 because we only have 1 mole of it, and 150 divided 3 is for Ag because we have 3 moles of it. And then we find that PO4 is in excess, whereas Ag is limiting or negligible, as they say. Yeah. Then to find the moles of concentration of all ions. Yeah, they want concentration of all ions. Oh yeah, it's negligible, by the way, because it's such a small number when you divide it by 3. So 150 minus 50. What's 50? 50 is the... Wait, where'd the 50 go? I had the 50 in front of me. Yeah, my bad. 50 is from 150 divided by 3, you get 50. So you have to minus by the limiting. So 150 minus 50, you get 100 moles left in excess, because that's... Or millimoles, my bad. So you're gonna do the 100 left in excess divided by total volume, and you get the concentration. Now let's move on. So we have a volumetric analysis is the technique to determine how much of a substance by using titration. Titration, we know it is when you want to see how much concentration of a titrant should be used to delivering from a burette a measured volume of solution of known concentration, which is the titrant, into a solution containing a substance to be analyte. It's just practically when you want to see how much is the concentration of something else. We use it in acid base usually. Endpoint is the point where the indicator just changes colors, because you have reached the exact point of where the two opposing ions like H and OH balance out. The equivalency point is when enough titrant has been added to react with the exact substance in solution being analyzed, which is practically, like I said, that point where the H ions and the OH ions are exactly equal. Now, acid-base titrations, at the end point, you have NH plus and NO, and the moles of H plus and the moles of OH minus are the exact same, equal. Now, let's move on to CQD7. A sample containing 25 centimeter cubed of NaOH was needed to neutralize exactly 20 centimeter cubed of 0.2 molarity HCl solution. Calculate the concentration of the base. Now what we're gonna do is we need to find how much moles of the HCl we have, because we need the moles of the OH to be the exact same. So the moles of the HCl were 20 times 0.2. Is it? Yeah. 20 times 0.2, you're gonna get, so 0.2 times 20 equals, it's like CV equals CV, by the way, exact same thing, equals we have here the volume, so equals 25 times how much concentration do we need? C. When you do it, you're gonna get that it's equal to 0.16 molarity. What volume of 0.5 molarity HCl is needed to neutralize 20 centimeters of 0.02 moles of CaOH2-2. What you're gonna do here is the exact same thing, but here you have 2 moles of OH. So we need 20 times 0.020 all multiplied by 2 equals to 0.5 times the concentration, or the volume, we need. Right? So yeah, see, Na equals 2. So we're gonna do the exact same thing. You're gonna get 1.6. Now we have a new idea. Balancing redox reactions in acidic media. let's see what this is about. Now, we have assign oxidation numbers for each element of the following element. Okay, yeah, very easy. O is always, except with hydrogen, except like this, it's always -2, except when it comes like this, then it becomes -1. This is the only exception for this. OF is -1 always, and since we have here OF2, F2, so -1 becomes -2, then you need to cancel it out because it's equal to 0. X minus 2 equals 0, so 2 is the O. This is... Oh yeah, these must be the exceptions for O. This entire question. Yeah, this question is telling you about the exceptions of when O is not -2. Na, also group 1 elements, I think, are also the same. Because here you have Na2, so it's 2 plus. Na is +1, but you need to add the subscript. So 2 plus X equals 0. So it's 2 minus -2. But we need for each O is gonna be -1. Now, HOCl. We know H is +1. We know O is -2. So since we have one of each, so 1 minus 2 plus something gives you 0. Plus X, my bad. So 1 minus 2 is -1, -1 plus 1. That's how you find. We should know these. Now when it has a superscript of -2, that's what you're putting after the equal. You're not putting 0. So we don't know C. Let's say we don't know C. C plus -2 times 3, which is -6, equals -2. So you're going to move this to the other side. X equals 4. So the oxidation number of C is going to be +4. And they're just going to keep doing this for the rest of them. We should know them all. Except SO4, I didn't actually know it was... Oh no, you need to find each one alone. You don't need to get it. So yeah, except here we have 2 unknowns. They won't usually bring anything like this in the exam without telling us. Or you could probably find it from the periodic table. But anyways, moving on. Again, N is known as -3, H is known as +1. You have to equate all of it to 2. And then you need to multiply each H and H by... And H you need to multiply it by 6. And N you need to multiply it by 2. So here you have -6 plus 6 equals 2 because the superscript. So we're left with X, which is Cu, and now these two cancel out. So X equals 2, so X equals 2. And that's it. Now we reached the long CQDs. This has 3 parts only, I think. Yeah. Solving these is really long, but hopefully they don't bring questions that are this long in the final, because I doubt the time is enough. A lot of the grade 11 said the exam was hard. But anyways, we're left with CQD 10, 12, 13. 13 is very long. I don't know why, but sure. And then you're left with also 14, which takes up an entire page for the question. But the solving doesn't look that long. Anyways, let's go back to CQD 10. Anyways, so you have F5 Fe2 plus MnO4 minus and plus 8 Ha plus gives you 5 Fe3 plus Mn2 plus and 4 H2O. Okay, so 5 was the Fe was oxidized because the superscript increased. MnO4 was split up. The O went from being -2 to staying -2. Nothing happened to the O. Mn went from being, so here it was Mn went from being 8 to 2, so it was reduced. So you have your oxidizing agent was MnO4 was oxidizing agent, and Fe was your reducing agent. Even though Fe got oxidized and Mn got reduced, but you always oppose them. Oh yeah, I did not realize that was the question for the first one. I did not know it was the question. Yeah, so like I said, MnO4 is the oxidizing agent, because Mn had a number from +7 to +2, and Fe2 plus is the reducing agent. Oh wait, I said +8, right? I didn't realize there was a minus up here. Anyways, Fe is the reducing agent because it's got oxidized. If it gets oxidized, it's a reducing agent, but if it gets reduced, it's the oxidizing agent. So the oxidizing agent, the oxidation number for Fe increased from 2 to 3. I did not realize that was the first question. Anyways, describe the color change when the point of titration has been reached. Now, we know that Fe2 plus produces a green color, whereas Fe3 plus produces a brown color. But here they said pink. Why'd they say pink? Here they said pink because we have water. Water balances out the color. It's gonna like I forgot the word in English. It's gonna like dilute it. Since it dilutes it, the color of the brown Fe3 plus also dilutes. Yeah, and the MnO4 color is gonna dominate. MnO4 color is gonna dominate. What? And the endpoint, both both are present, but the color for MnO4 is gonna dominate over the Fe. Yeah, anyways. Now, see, what the effect was adding less, V on the experiment determined the mass of the percentage of iron in the compound. What they say here is that the volume, what's V? Wait, less V. Let the variables G, M, and V be defined as follows. V is the volume of MnO4 added at the E. Okay, yeah, finally I found it. So our volume, so they must have mentioned the volume somewhere up here without me noticing. No, they didn't. Sorry guys, I had a problem. Anyways, again, the effect of adding less volume of MnO4 to reach the endpoint makes the volume way too small. So the moles needed of MnO4 is way too small to have the because we calculated a small number of Fe2 plus. So moles of or mass of Fe2 plus is also too small. What they're trying to say is when you decrease the volume of MnO4, you cannot produce enough Fe3. You won't have enough 2 plus because we don't have enough 2 plus, and if you decrease the volume, we won't have enough to make all these products. I think that's what they were trying to reach. So the number of so the moles of Fe2 plus, you need to divide them by 5, which is the subscript. Coefficient, and NO4 you need to also divide by the coefficient to get it. And then if you divide it by the coefficient, guys, I swear I'm trying to understand what they meant here, because what they're trying to reach, because this part I did not understand at all, is when you decrease this will also decrease, and it will not be enough. The percentage of the mass, percentage by mass, won't be enough. So the volume is less than the corrected volume. And that's it. What volume in milliliters of 0.1 molar potassium manganate solution is needed to completely oxidize 10 milliliters of 0.30 molar copper nitrate solution? So we need to write down our equation. Completely oxidize. So CuNO3 must be oxidized. And you need how many? I think this was given. Yeah. So you have the potassium permanganate, which is KMnO4, which wasn't given here in the equation. Probably wasn't given because it's not a reacting ratio. It doesn't react with anything. So anyways, so you just need the volume. Now we need the moles, and to get we need the volume or the moles per Mn. Okay, yeah, I got what they want. So you need to find the moles per 1 ion. MnO4 you need to divide by 1 because there's only coefficient 1. Cu you need to divide by 5 because the coefficient's 5. So the MnO4 multiplied by the volume, the concentration multiplied by the volume, you need to divide it by 1. and the copper concentration times the volume, we need to divide by 5. We know that the concentration of the potassium permanganate is 0.10 times the volume divided by 1 equals the same thing but for copper. Divide by 5 because we have 5 moles and here we have 1 mole. So 0.3 times 10 divided 5 equals 0.1 times V times 1. So the volume needed is 6 milliliters to the correct significant figures. And yeah, they're just telling you why it's the two significant figures. Now, oh yeah, and coefficients can't have decimal points, by the way. So it's two significant figures because of the givens in the question, not because of the coefficients. Anyways, now let's move on. Top questions. Okay, so let's put all this question almost in a page. Yeah, this question takes up 2 pages, so here. This is the entire question. One of the lab experiments in grade 12 is gravimetric analysis to find the mass percentage composition in alloys. During such a laboratory session, students were given an alloy of lead and gold, so PB and AU, and asked to find the mass percentage composition. So they gave them this acid, nitric acid in concentration 15 molar, 5% base of NaHCO3. Is it the base or I genuinely don't know. KBr, which is an aqueous solution, distilled water, and they gave them graduated cylinders, which are 100 milliliters, a beaker, which is 100 milliliter, a dropper, a stirrer, goggles, and safety gloves. They prepared 100 milliliters of 5 molar HNO3. Then they dissolved they dissolved this much of the alloy in the formed solution of the HNO3. They filtered it, and then they added saturated NaCl, which means that the NaCl is in excess in the solution, to be collected, filtrate till no more precipitate forms. Yeah, they kept adding until no more solid forms, till it's in excess, the NaCl. Filter the resulting, then they washed it, they dried it, and they found the alloy percentage. What's the volume of 15 mole HNO3 needed to prepare 100 ml of 5 HNO3? So it's CV equals CV. So 15 times V equals 100 times 5. So we need 500 divided by 15, which is 33 milliliters, because we used millimoles here. Anyways, now using only the material found on the bench, briefly describe the procedures needed to prepare the 100 milliliters of 5HNO3, include your steps and the apparatus and the safety measures. Now, to prepare the nitric acid, did they tell us how much nitric acid? They only told us the R. Oh yeah, they said prepare 100 milliliters. So you need to wear the goggles and the gloves. Always safety is your first step. Then you need to use one of the measuring cylinders to measure 33 milliliters of the HNO3, because this is how much we need to dilute it or to get the 100 milliliters. So you take 33 milliliters of the 15 molar. Then you get the other graduated cylinder, or sorry, you use the second, there's no second graduated cylinder, it's only one. Oh wait, sorry, graduated cylinder, my bad. So you use the second one, and you measure 67 milliliters of distilled water. Why? It's whatever is left. You need 100 minus this in water. Then you pour the water into the beaker. Then you put the acid over the water and stir. That's it. So what you just need to do is you need to find how much volume of the acid you need. Then you dilute it with whatever is left of water to reach the volume you had here. Now, part C, the students did not find a 100 milliliter volumetric flask on the bench. Why was the volumetric flask needed? Justify why the volumetric flask need not to be used during the dilution process. It's because the graduated cylinders measure volume with two significant figures, and which is way more than enough for a precision, making the volumetric flask way too precise, and you don't need this much precision. It doesn't matter. Anyways, so just telling you that the volumetric flask is way too precise, which we don't need in this experiment. Now, while checking the groups working with the teacher, when checking the groups working, the teacher notices that one group spilled a few milliliters of the nitric acid on their bench. The teacher immediately asked the group to clean it up using what is on the bench. Which of the provided liquids is the best option to clean up the spill? The best option to clean up an acid would definitely be a base. So the NHCO3. Yeah, it's a base and an acid will neutralize to form water. So it will just form water, which is the safest option. If you clean it with water, all it's gonna do is dilute the acid, while just keeping acid. There's still gonna be acid, but it's gonna be diluted. When you add the base, it becomes water. So that's way safer than having acid. Now, part E, find the percentage of mass of the alloy sample. Now, okay, so you have the mass of the lead gold alloy sample. You have the mass of the dry filter paper. You have the mass of the filtered paper and precipitate after 5 minutes in the oven, after 5 more minutes, and after 5 more minutes. You're gonna say, why did you only do it for 15 minutes? Or why did you stop after doing it 3 times? It's because here there's no significant change. 0.0001 gram isn't significant enough for you to repeat it for 5 more minutes. So that's why you stopped after 3 minutes. So now, the mass of the PbCl2 is gonna be 29.4622 minus the amount in the dry filter paper. So you obviously need to take the amount that's final and subtract it from the amount it was initially. So after the 15 minutes in the oven, you just subtract it and you get... What the hell happened? Oh, you can move. I did not know we can move it. Anyways, I need it to be... Where did I go? My bad, guys. Yeah, there we were. So you're gonna take the amount it was at the end and the amount it was in the beginning, subtract them from each other, you get 0.7 something. Yeah, here. 0.7102 grams. Then you find the moles. How do you find the moles? By dividing by the molar mass, which is this. You can find this from your periodic table, of course. You get this many moles. Now, the mole of NPB, Pb2 plus, is going to equal to the moles of the entire thing because the coefficient is 1. So the mass of the Pb is just going to be the moles of Pb times the molar mass of Pb gives you the mass of Pb used. So the percentage is the mass over the mass of the sample, not the mass of the dry filter paper with the precipitate and everything. No, it's only the sample, the percentage of mass. So if this is this is the mass of lead, you divide it by mass of alloy. It keeps moving. Mass of alloy. It's just practically just what they did here. After that, you multiply by 100, you get this much percent for Pb, and then when you subtract this percentage from 100, you get the percentage of AU. And that's it. Please tell me there's one more question left. Yeah, there is, because this video is way too long. Anyways, during a lab session, a grade 12 student had some tablets on their station. Teacher explained that the tablets contain sodium fluoride, NaF, and some impurities that are water soluble. The students were supposed to determine the mass percent of F- in the tablets. So the one group of students decided to dissolve it in water, then add the above solution, which is NaF, into an excess of CaCl2. Then they filter the CaF2 precipitate because it forms a precipitate. Then you wash it then you determine the mass, and these are all the masses they have collected. And yeah, write the balanced net ionic equation for the precipitation that occurred, which is adding the Ca to the NaF. So we know that it produces a CaF2 precipitate. So the only two ions that we need are Ca2 plus 2F minus gives you CaF2. And that is it. Of course, add your the solid liquid, I forgot their state symbols. Add the state symbols, of course. Now, why did the student repeat the drying and weighing step? Because you need the difference in mass to be insignificant. You need all the water to dry. Like I said, 0.001 gram is insignificant. Oh wait, is there a second part? Oh, sorry, I didn't see the second part of question A. Why is the net ionic equation a better way than other representations? Because it only shows us what we need. Whatever we don't need, aka spectator ions, are ignored. So I did not see this question, but yeah, it's very obvious. Okay, so why did you? Because it must be repeated, so you need all the water. When the mass becomes constant, all the water has evaporated, you can stop heating. Part C. Which is expected to have a higher concentration of the filtrate? Na plus or Cl minus ions? It's obviously gonna be the CaCl2 because you kept adding it in excess. Why do you add it in excess? Because you want to add it until your precipitate stops forming. Because you want all the F to finish from the NaF2. Or NaF. So you keep adding CaCl2 until NaF or all the F minus ions are done. So the CaCl2 is going to be added in excess. So you're going to have more Cl minus ions than Na plus ions. Now, D, determine the percentage of F minus by mass in the tablet. You're going to have to find the mass of the CaF, which is, you're done by, here. You get the final, 1.745, subtract it from the initial, which is 1.462, you get 0.283. Then you divide it by the molar mass of CaF, this many moles. Now the molar mass of F minus is going to be the same as 2 of CaF2. Why? Because you have 2 F minuses. So you're going to multiply this number by 2 to get 7.25. Then you're going to multiply it by the molar mass to get the grams, and then you're dividing the grams by the alloy's mass. This is the exact same question as the one above it, by the way. And now part E. A second group followed the exact same steps, but decided to dissolve the tablet in 100 milliliters instead of 60. How does this change affect determine the percentage by the group? It's gonna be the exact same as the first group because it's the same tablet and the same alloy, and the extra water is just gonna go when you evaporate it and dry it, so it doesn't really matter. Now, a third group decides to follow the same steps using the 0.5 instead of, they use just a different compound. Will the third group be successful knowing that KSP, what's KSP? Okay guys, so the KCP is the solubility constant. So if you have a small KSP, it's very insoluble. So what's written here in the answer is, like it's written, the solubility times 10 power negative 18 is a very small number. So SCF3 cannot mix, it's insoluble. It will precipitate whenever NaF and CSNO3 are mixed. So the third group procedure will be successful, like there will be a precipitate. So yeah. Now, what's the third group? The third group were given a single tablet to run their experiment. The balance they used measured masses to the nearest 0.01 gram. Will they be able to report this mass to precipitate to 3 significant figures? So we have to calculate the mass. We have the moles here, and you have the moles of F, and to find the moles of NSF3, you divide the number by 3, because I'm assuming in the equation somewhere we don't have an equation. but you divide it by 3 because SF3, you know? So 2.42 grams times 10 power negative 3 moles. To find the mass, you multiply by the molar mass of SCF3. You get 0.247 grams, and the mass of the precipitate is less than 1 full gram. So if with the given balance, you can't put it to 3 significant figures, you have to put it to 2. So because here it could show you to the nearest 0.01 gram. It's less than 1 gram, so it is significant at this here. So you can only put it to 2 significant figures with the given balance when you need 3. So yeah, and I think that's it for this chapter. We're finally done this chapter. Hope you understood everything. I'll be uploading chapter 5 later on today. Have a good day. Bye.